Right, so welcome back, and from now on, we're going to conduct class online. So that means I will post my lectures online, making videos and upload it, and then post it on Canvas. So that's what I'm going to do. I'd like to hear your feedback on this as well. You don't have to come on the exact class time. You can go through this anytime you want. So. So that's how I'm going to conduct this. Okay, right. Anyway, right. If you have questions, please email me, or I can make an announcement on Canvas so you can reply for those things. So if you have issues, so let's talk about particle systems. Right. So the particle systems. Um, So one important part on this is why we're using particle systems. What is the purpose of that, right? And well, if you're using the things that you cannot do with the other models, like simulation of fire, right, or the water flow kind of things, the clothes movements, the hair, and things like that. Actually, those are very expensive operations, right? That is where when it comes to rendering those kind of things, uh, the machine has to run a little bit extra mile on rendering things. So we have to have a better organized method to illustrate those things. So that's why these particles are introduced, and especially is using for these kind of things like modeling fire, smoke, water flow, right, cloth movements, and rigid body dynamics like hair and all that things. The wind is another one, right, and so on. So it will be useful when it comes to pretty nice dynamic effects actually. So it is blending with actually if you're writing in OpenGL, the blend functions will be very important, and then if you're writing this in using a GLSL, which is the shader coding, mostly is a good friend of these kind of the, the systems, right? um, why? Well, the reason for that is we're talking about here in the next slide. uh, so the particle systems is a system to control collection of individual elements. Okay, so yeah, it can go, so these individual elements right here, right, that is the one part. So what are the individual elements? It can be points, right, it can be lines, it can be triangles, of course, right. So the point, line, or a triangle, or obviously as texture, right, this little quad, right. So that means you can either get dots like this, a lot of them together, right. So that is the point, or you can get lines like this, right. So that is also addressed as a particle, and then either triangle, right, pieces like this, right, or a sprite is a picture. Obviously you will have some image in it, right. It's like smoke or fire. Usually that's what I use usually. Anyway, so those are the things that you can get, especially when it comes to these quads. Well, those are small quads, like this together, and it's moving on some order. Like for example, if it's a fire, you just set up a path like this, and then setting up like that. Points, you can use something else like that. But anyway, so this is the idea of particles representation is this. So we're going to talk about this in a minute, a little bit more further. But the thing is, these are actually acting independently. So acting independent is very important, one factor. So that means you're going to give some properties to this, maybe the position, so the each one has its own position, right? Or the speed that you're moving upward like that. So how fast you go, so those are independent properties as well, and for each one. And then the color, of course, if you're using just the point, maybe you can set up RGB values onto this, right? RGB value onto this. But if you're using the sprite like image, so this is just an image render onto the quad, right? So you already know these things now. And then yes, if you're setting up something like fire, so starting, there's a fire start here, and then what happens, it will go move up, and maybe the scale and the shape will change, and the position will change, right? It's getting bigger, right? And then again getting smaller, right? And it's still moving like that, and then it's getting very small, and then you say it's dead, right? Or it's just evaporated. So then what happened? So what happened after this point, which is at the end? So that is why we just addressing a lifetime. That is one thing that we do. And then shapes and sizes, obviously, you have to apply that and see how this thing appears on the screen, right? I mean the particle appears on the screen right here. So you'll have a small size, make it bigger, and then make it smaller if you're simulating the fire, kind of things like that, right? So those are the things that we can play around with particles. Okay, so this is the process steps for particle systems. Obviously you have to have a random generator, and then something called emitter, and then something called updating your everything, right? So what is this random generator does? So let's talk about that first. Okay, so especially the random generator, so this one right here, right? What does this do is, well, the particles, you can have many number of particles, right? Some ones that we have seen the examples have 1 million or over, right? Dots or the things like that, right? But it doesn't mean that you have to generate all 1 million at the same time. So this means I will have some way of generating and producing actually the particles at a time. So maybe I will take one portion out of 1 million or the 100,000 or whatever the number that you have. So I will produce portion of it at a time, right? So you don't need the whole number at the beginning, right? So if I have this in a stack or an array or whatever it is, maybe I will say, okay, I'll produce this one, I'll execute this one first, and then I release this one first, and then when they expires their lifetime, obviously I can put it back, right? And then execute that again. So like that. So you can if you don't have enough particles to show here, you always generate them, right? Once their lifetime is expires, they again come and reset their lifetime here. So in that case, it's a cycle, right? So this is a cycle is going on, right? Like that. And in this cycle, the one part is this emitter. What is the emitter does? Well, whenever you say you give a birth to a particle, right? So when you start up a particle, you have to give some initialization, initial size, right? Initial size, color, right? And you say, okay, the lifetime started right now, so the life factor, and so on. So you will know what will happen to this particle when it's moving. So actually initialize the position as well, right? As position x, y, z, right? So then this is to setting up everything, which is to this particle. We do it under emitter. Okay, so this is what determine what you should give it to this particle, or how you dressing up this guy, right? And then the time being, so you're going to render this, right? Or you can change its values when it comes to the stage of update, right? So if it is the initial updates, no worries. So then I'm going to render it, and then in the meantime it will move up in the position. Maybe I'll make it bigger and change its color as well to something else, right? And then now it has this shape instead of this shape, and so on. So then I'm going to change my position, size, color, and the lifetime also. You're going to update those values. So you're updating the values. So this is where the updater comes in. So this is what it does. So you update everything in there. Okay, so then after you update all those things, again you're going to draw this into the screen. So the render means you're drawing things to the screen. So this is what it is, right? And then after you render it again you'll do some movements onto this, and that means I'm going to update this data, the position, size, and everything. So then, and so on. So this cycle will go on until it expires its lifetime. So then after you're done with it, you can put it back, whatever you want. You can set up its lifetime as a boolean value and then come back, right? So anyway, so there are so many things that you can do with it, right? So yep. But anyway, so that is the one part that you can do, and let's move on to the next one, right? Okay, so this is what I was talking about, right? What is each part of this doing, right? So the generation of particles is, we call particle the generation particle is randomly within so this is actually the generator part right here, okay? And then well, the particles, of course, it will change its behavior, whatever you want to do with it. So that part comes in. So dynamics, particle dynamics, you call it, right? The size, shape, color, and whatever it's changing, right? Depending on what you're using. Maybe if you apply a collision, it will behave differently, and so on. So there's so many things that you can do to these particles depending on the application, right? And then obviously, yeah, the age of the, you call it maximum lifetime for the particle. It is not necessary, but mostly you do that, or you can reset it back to whatever its value. So that's what pretty much we do, is resetting its values, right? And yeah, there are other extinctions that you can apply instead of a lifetime. Maybe it will move out from your boundary of particles. Let's say you have a boundary or a box, and if you just go out of that box, if you have a little particles here, and somehow it is going out of the box or hitting on the other objects, depending on the application again. So you can reset it back, so somehow, right? So that is that, right? So that's the lifestyle. I believe you understand what I'm meaning, what I mean here. And then the data structure in C, usually we are using something look like this. You can write this as a class if you want, but I'm a C guy, so I'm just, I like to stick with the basic. So that's why I'm just using this. Well, the gravity, velocity, and things like that, especially it comes to when you having a physics applications. Like, um, so we're going to look at some physics applications using particles. Um, why is it important? Well, you usually uh, making the natural phenomena, right? Like wind, fire, and things like that. So, especially that is what particles use for, right? Especially in gamings and stuff like that. Um, so the gravity take a big role on it. So that's why if you ever heard the GPU, especially the NVIDIA ones, GPU has the physics X engine. So that is also helpful for you to do these things. Okay, right, and yeah, so you can have as much as you want. You can have any any number of elements and properties here. The only thing here, when if you're using it as a data structure, obviously with a class you can set it as a private elements with a one name, which is particle, and then you give a name for that, right? So yeah, making it as a data structure is helpful either way, right? But I know some people using the classes because that makes your life easy. You can have many instances you want, right? In this case, if you're having a particle like this, obviously I had to make a particle array, right? So particle a of 100,000, maybe, whatever, right? So if you create it like this, each element has all these properties, which is position, direction, forces, speed, and all that. So this is a0 has that, and then also a1 has all these properties: position, direction, emitter direction, forces, speed, mass, age, and lifetime. So like that. So you'll have 1,000 of them. If you have 10,000, of course you have 10,000 of them. Has all the properties, right? So that's the good part. If you either you're writing it as a class or either writing it as a data structure, one way or the other, this is what you end up with. So then you will update these values, each of these values, or if you're using equations like what we're going to look at the next slides, you can use that, right? So what is the best data structure to store this, and how are you really going to manage this? Well, one thing is these are just the recommended ones, not actually you have to stick with these, right? um, well, so the stack is all right, right? But anyway, whatever you use here is anyway, both are arrays, right? Right. Even when you're talking about heap here, right? This is a heap means what? What is heap? Heap is a binary representation. Um, I mean, the array representation of a binary tree, right? Complete binary trees. That's what heap is, right? That's what they're talking about. But anyway, I believe you learned that in data structures and algorithms, right? So yeah, if you're using this kind of a data structure, you have much more control what you want to execute or how you want to manage things, right, than this, because this one has uh, well, if you have something like this, it is the lasting FIFO, or yeah, so this is, you have some limitations to use this, but it is easier obviously than manipulating or handling the heap structure, right? But the heap structure they recommend is better in most of the things because you can travel fast, throughout the things, the particles that you have, or you can handle particles much better than this structure right here. So this is easy versus efficient. So that's what we're talking about here. Okay, but all the particles are not strictly force you to use any of these structures, but when I'm writing my own particle engines, I usually use heaps. That is nothing but an array with some order in it. Okay, but you can just throw it in there. We'll do a lab, so we will understand how you're going to do this. Okay, right. So let's move on. Right, and so um, so this is something that when you're writing an engine for particles, what you're going to do. So usually um, you generally using these kind of steps. Here it says, yeah, in a one time set you have to update everything. So these are things that you do, whether you want to make it live again, the birth and death. So this is actually a boolean value. So you can have a boolean active or not, right? So that's what it is, right? If it is active, you can say it's reborn or the structure like that. You can set it up, and the death means is inactive, so it is false. If it's active, it's true. That means it's live. So more than birth, it is just a live and death situation. The birth means you just reproduce something. I mean, initialize it, reset it. So that's what the birth means. Okay. Right, so the velocity operations, of course, if you are using something with the physics, you may will address these things right here with the force, the collision, and the damping, right? What is damping? Well, so if you know, the best thing I can introduce damping is pendulum, right? Oops. So pendulum, right? So you have a little ball here and then a string, and then you let it go, and then it will swing like this, right? And then you swing it back, right, like that. So but sometimes it will go up and down like this in this motion, and then it will stop, right? It will come to the stop. Alright, so what causes it to stop is we call the damping on the string, right? So there's a there are some atoms or whatever. If you go to that level, those are brushing each other, produce some energy in it, right? So this energy will consume whatever the kinetic energy it's producing. So anyway, so if you move something like this, it will go up and down and stop. So that is what causing by the damping of the string. So that's what the damping is. Okay, like that. If you having some like the first lab we did, we have a little ball and then it's bouncing everywhere, right? As whenever it's collide with the background or the walls like here, it will reduce its speed, right? So that is the collision effect we're going to talk about. So you can have changes velocity because of the collision. And then the forces, of course, if you have one ball and hitting to another, that is changing the force between those two. Usually using F equals ma equations on that. So those are things that you have to think of, right? Right. And especially one thing, this is only if you are considering mass. Usually in particles, if it is a small thing, usually we don't use mass. If you don't use the heavier side of it, Usually, if it is really small, what I mean is using MV instead of MA. So we'll address this a little bit when we come to the equations. So keep please be aware of this. This is another equation for the smaller things. If it's the bigger things, of course, you can use this equation right here. Right. So this is for considerable mass. But if you really have a smallest mass, usually using not the acceleration, it is the velocity. And position operations, of course, depending on all these collisions and everything, you have to update your position of it, right? And then alpha blending, these things are, especially if you're using a fire kind of thing, if I want to mix these the sprite images and just make it look cool, fire look like this, right? Instead of you showing just the squares with the pictures like this. So this is where the blending comes in. So there are some blending operations we're using, especially for the PNGs. We're using this when you're using OpenGL, right? Source blending, comma 1 minus source, I guess. So that's what we use, especially in PNG, right? Right. So the blending functions comes in and then make it look pretty cool. And alright, so what is this? Transfer pixel to vertex data. Well, that is something to take care of the colors, obviously, right? The pixels are RGB values, right? And the vertex data is, if you're using a point, line, whatever it is, just have some data on the positions and everything. Right, the vertex is XYZ, right? Pixels is RGB, right? So what that means is whatever the RGB on the screen or the color, that we have to take care of handling the colors. So this is nothing but we just handling the colors between those things, right? And then rendering, obviously you have to render each step, right? So if I have my particle here, I will render that. Next step, particle right here, the bigger shape and the color, so you render that. And each time step, obviously I have to do the rendering, right? Okay, so let's move on. So what are the motions or forces you can apply to these kind of things? I'm just going to touch a little. It's not going to be strictly that, but mostly the projectiles. If you're using projectiles, this is what it is. Well, I'm sorry about the typo up there, and but anyway, so this has to be motion, has to be somewhere here. So this is a one type of particle movement. This is actually if you want to have a water fountain of things like that. So you consider the alpha angle here, and there are two forces working on it. So actual force is this way, that's the moment. So usually when you're having something like this, you break it into two pieces like this, right? So this is the cosine value of this. So in the velocity on the x direction, we call it v0 cosine theta, or alpha in this case, right? And then the force towards upwards like this, we say v0 y, right? Y, that's the sine theta, right? That's the sine theta. So how do I come up with these values of sine theta, cosine theta? Well, you can see here, this is actually a triangle. If I draw this like this, it's a right angle, right? An alpha angle here, right? Okay. So how do I know which is a cosine is? So, well, this is the vector I have. We learn vectors, right? So if I divide these to two different vectors, one is going upward like this, one is going this way like this, right? Okay. So how do I come up with these values? Well, so this portion here is we call let's say it is d value, right? Okay, or in this case we call it v0, right? Okay, so that is the magnitude of this, right? So one thing I know is this part right here, right? Let's call this x portion of it, right? Okay, so this means the cosine theta is going to be equal to, right, x divided by v0, right? And we know and so the y part, which is this part right here, right, you can say sine theta is equal to y divided by v0. So that's what the equation for sine and cosine, right? So in this case we have to know what is the this portion, which is this part right here, which I call it x here. So the x will be equal to v0 cosine theta, right? So why? Well, I can move this one this way. How do I do that? I multiply this one by 0, multiply this one by v0, this to this cancel out. The x is equal to v0 cosine theta. So is this one, can do this, right? So this to this cancel out. Y is equal to sine theta v0, right? So that's how I get these values, right? So so this is breaking one vector into two vectors, right? So that is how you represent the forces on these two directions. So why we have to do this way, right? So one good thing is, if you're using a physics, the gravity is always, we call it downward, right? That's the gravity. And so gravity has nothing to do with this direction, because it's a 90 degrees. So there's nothing I can apply, I have to apply for the v0 portion of x portion, right? Okay, so I don't have to worry about that. But for the y portion, obviously, so this is x portion, so anyway it's going to be v0 cosine theta or alpha. And I'm sorry, if this is theta, this is what this means, okay, right? So in this one, which is, if I'm talking about my other way, right, actual force on this direction is going to be whatever I have there, which is minus g. So those are the forces I had to apply on this direction of this, multiplied by whatever the force, maybe m here, right, or whatever, right? So anyway, so this is the part, in this case this is mg. So this is the part that we have to consider when you're talking about the forces on the upward direction, right? Again, I said when you're using particles, you consider the velocity instead of acceleration. So in that case, we have to consider how we're going to apply that to g. Maybe g has no much effect on things which is going upward, right? But if you're using something something like the heavy object, like a ball or sphere, or maybe if you're thinking of something like a projectile on the shooting some object like this, right? So in that case, yeah, the mass matters, so you apply something like that, but not always, right? Okay, so how are we going to do the x and y using this equation on the displacements? So this is what it is actually. This is a projectile equation. So the x moment of any object which is moving on the x side, we call the time is t is the time, and cosine theta. So for the y portion of this is always going to be vt sine theta minus half gt squared, right? How did I come up with these equations? Well, that's physics. I don't want to spend much time on it. Just take it as a grant. How we can calculate this actually, if you apply the distance over time as a velocity and all that. Okay, so this is actually the distance over time into the values of the portions of the vector directions. Okay, right. Especially we are applying the gravity in this case. Right. So this is just a projectile motion of something. It's moving like this on theta angle, and then the initial velocity is the one which is v0. That's the initial velocity, right? While it's moving, well, it changes. So that's what it means. It always changes. For the portion which is going upward, the gravity has influence. The portion which is going on this line, we don't have to worry about. Okay, right. Anyway, we'll try to apply this on our labs when we're writing something. Okay, so again, each particle is has an ideal point mass. So if it is a point mass, of course you can use either F equals ma if you are considering higher mass. Otherwise you're using mv for the smaller things like very small particles. And so this is called Newtonian particle. So this is something that if you want to apply on your simulations, you can have individual points and then apply some behavior on this these kind of things, right? So I'm not going to stick with these much because this is much more into physics than computer science. How are you going to play around with particles? That's what I'm talking about here, and as well as right here. So this is another one which is usually the equations for the particles. Obviously there has to be comma here, which is we're going to talk about. X, y, and z position of each particle, and the changing of velocity is nothing but the position over time, right? So this is a smaller change on the position over time, position over time, and position over time, which means if I have one particle movement on this, I'm going to divide that to 3 dimensions, right? So let me have this is the movement of particle, and then these are the dimensions, right? Okay, so this is z when you're looking at 3D, right? So this is 90 degrees on here, 90 degrees on on here, right here. So this is actual path, which is starting from v0 and moving there, and this is z-axis, y-axis, and z-axis. I mean the y-axis, x-axis, and z-axis. So you divide this to all 3. So might be moving some distance here, some distance here, and some distance here. So those are 3 distances that I can apply as a x di over dt for a given time is this distance over time, right? So that is a velocity, and movement on this, which is z, is nothing but I can say zi. Actually there's a typo here again, it has to be d here, right? D zi over dt, right? And for this part right here, it is dy over dt, right? So yeah, so that is how if you want to set up your velocity calculations on this, the moment. So this is a particles equations, especially for small objects. So that's why I said this is using mv instead of ma. So that is the equation we are talking about right here. Okay. Right. So so that's what it is. If you're using a particle This is not that hard to do this, even to say defining the force vector, right? Um, oh, well, these are just taken from some of the computer graphic book, and so, but it is not that hard. We'll do this in lab and see how it works. Right. So the how particles are displayed on screen. Well, you can actually we talked about that earlier, right? The points, obviously, that is one way of doing these things. And then the lines, of course, I can have line portion, especially if you're having a hair, you can have pieces like this together. So you can look at it like this, right? You can remember when we drawing a Bezier curve, we draw it with the points, I mean the dots, like the ones we have on the top, right? I mean the points. So that's one thing, and yeah. So the other one is a sprite, which is a quad with a little design in it, right? And then again, I said if you're using a geometry, usually you can use, especially if you're using a geometry shader, you can use this one as well, right? So either way, so these are the ways that you can represent things, especially if you're using a water kind of simulation. This is the mesh as connected with each particle closest neighbor. This is called using a spring mass system. What is this used for? Well, there are two things: either water simulations, you can use this particle behavior, or you can have this for the clothes as well, right? So those are things that you're using these kind of particles. In this case, you don't have lifetime things. Yeah, you can apply that, but mostly you don't. This is if you simulate a clothes or the hair movements, or the clothes. This is especially the clothes kind of simulation, or the water, right? Using particles. Well, and in those cases, we don't set up the lifetime, right? It will be moved forever like that. Okay, so that's the one thing, and the other is a spring mass forces. Well, if you know the equations of Hooke's law, which is a distance, I mean the force on, I think it is, yeah, the force is equivalent to constant time, the distance, the displacement. If you pull this a little bit on the distance, the force, restoring force on this spring, if you pull this way by s distance, is depending on the force on this will be depending on what the force will be depending on the constant, where the material, the spring is made of, multiplied by the distance that you have. So when if you want to calculate the position of the particles, which is bumping up and down like this, right? You can actually generate the force divided by this k guy will give you the position or the displacement. So you can use this equation and move your particles up and down like this. If you give some force into that, well, it will be motion, will go like this over time and will stop. If you don't have a damping on this spring, if it is not heating up and if it is moving very smooth, this will never end. In that case, the motion will be look like this. It's never going to stop. It will go like this. But if you are applying the damping on this, motion or the distance of the displacement will go and stop like this. What does this mean? Well, it means distance. It will move from here to here and over time. Okay. Right, so those are things. If you're using a spring kind of a movement for the particles, you can apply that as well. Those are pretty neat ones that you can apply for each of it. And Well, people do so many things using particles and then play around with it. So we'll do something as well. And I think that's all uh, in this lecture I had to cover. But mostly the things that are very important that we're going to cover is we will do some labs on it and then see how the particles engines are generating. We will write something from scratch. Maybe if we have time, we can apply some shader coding and see how cool stuff that we can do with it. Okay. All right. So let's move on. I think we have. I have. Yeah. This. Right. Move to the next one. And move to the next one. And let me see whether I can open this here. So this is the link that shows the behavior of each. So I think we have seen this one. I have seen this one. This one I did not see. So that is also one way of showing particles, especially explosion kind of thing. So this is one way of its behavior. Of particles. In this case, I think their objects are 3D kind of things, and then it will generating. So you can see it's there's a generator, emitter, and then update, and then rendering. So all this you can imagine when you're looking at this, right? So this is one of those things that here you can do with the particle engine, right? Okay, so I'll close this at this remark, and then we will talk about I'll give you a little introduction on shader next time, and then we'll move on from there. Okay, all right, I'll see you on another lecture.